Stanford University.
Thanks very much. I appreciate it. First of all, my condolences to the Lady Cardinal. Unfortunate. 1 point, huh? Bummer. Okay. Well, I hope we can. What are you shaking your head for? It's okay. I like basketball too. I want to talk about concentrating solar power. I often start these talks by saying, you know, we're the other solar energy technology, the one that you don't hear about very much, because when somebody says solar energy, what's the response? It's photovoltaics, right? But this is solar thermal electric power, and it's a little different. But let me go ahead and I'm going to give you just a brief overview, a little bit of background information. I'm going to try to talk you through sort of what's happened over the last 30 years and where we're, and kind of try to point to where I think we're going. I'll also bring up what the current status is as I see it of the technologies, talk a little bit about cost and resource, and list some of the deployments that are ongoing right now, because that's really one of the exciting things that has changed. And then last, I'll talk a little bit about R&D directions. I'm obligated, I guess, to tell you a little bit about Sandia in case you don't know about Sandia. Sandia's background fundamentally comes out of the nuclear weapons program. We have a large activity in energy, climate change, and infrastructure security, which is where we're located. A lot of, some of you know about Sandia because we have a part of our organization here at Livermore. And in fact, one of the activities in our group is done at Livermore, a lot of the thermal storage work. But we have a lot of basic science areas to draw from. We pull from all those capabilities into the energy area as well. It's a strength that our lab brings to the DOE program. A lot of PhDs and master's students. If you're interested in a job in energy, let me know. Moving on. Okay, let me talk about the National Solar Thermal Test Facility, which is where my home is. We work with the DOE, and I'll talk about that in a minute. But from the point of view of testing, we have a 5 megawatt power tower where we've done testing on over 13 thermal receivers over the years. Most recently tested a falling particle receiver. We also have a solar furnace where we're currently doing a lot of work in what's called solar to petrol. It's S2P. The idea being that you can produce a syngas directly using a thermal process and use that as a feedstock for creating a liquid fuel. The advantage here is this isn't a batch process, it's a continuous process and could potentially be scaled to power tower capability. So there are a lot of things that could be done. This is actually an IR&D project internally funded by Sandia. We have an engine test facility where we test a number of different types of Stirling engines. We have a number of Stirling engine systems on site, both free piston and kinematic. And we have a rotating platform for testing trough collectors. We can test them at temperature and get the total optical performance and cosine losses. We work with our colleagues at NREL in support of the DOE Solar Thermal Electric program, STEP, a solar program. And we do all kinds of things. And we do a lot of, over the years, we've done a lot of industry support. Industry support's been important the last 10 years or so because the industry has been trying to deploy systems. In order for them to be successful, they've got to sell energy. And so we've been trying to support them to get there by addressing issues that occur, helping them deal with some of the problems that they find in the field. We do a lot of systems analysis, and I'll talk about this a little bit later. And obviously we do test and evaluation. We look at a lot of market development activities by providing tools such as market penetration tools that can predict what solar might do in the future if given the proper incentives. Our friends at NREL are doing a lot of that work. We find ourselves serving a lot as reality brokers because while we're proponents of the technologies, we're one step removed. And we can actually provide our own our own views on this without, so investment bankers call us and we say, well, we don't do that. We don't pick winners and losers, guys. But what we will do is we'll tell you the difference between a trough and a tower and what we think the relative strengths and weaknesses are, and then you can go from there. And so that's the kind of thing we try to provide. Okay, so what is CSP? The term concentrating solar power was coined about 12 years ago, I guess. It's really solar thermal electric power, and many of us really prefer to call it that. But this has gathered some steam and is now used internationally, so we do use it. It comprises 3 generic system architectures that I'll describe on the next slide. Fundamentally, it's a thermal process. You're collecting the sun's energy, converting it to heat, and then using the heat to drive a heat engine of some type. Typically, because of the cost to build these things, you need scale. So typically, we're talking about central generation, and typically, we're talking about systems that are 100 megawatts or larger. And that's important because you can't do these things at small scale in any cost-effective way. One of the key differentiating characteristics of CSP systems, particularly troughs and towers, is that they're capable of providing dispatchable power by using thermal energy storage. And I'm going to talk a little bit about that. In terms of building systems, we're dealing with mainly commodity items, pipes, glass, steel, pumps, power blocks, a few specialized items in terms of receivers, in terms of maybe the way the concentrator is made. But for the most part, they are commodity items, so the price points are easier to reach. And last, it's become increasingly important, and many industry providers are utilizing dry cooling for these plants, because where are you going to build them? You're going to build them where you have the most solar energy available, the most direct normal solar energy, because these systems use only the component that comes directly from the sun, not the diffuse components. And where are those located? They're typically located in the desert regions of the world. And what makes a desert? We don't have water. Okay, so while many of the initial plants and the plants in Spain certainly are all using wet cooling, but for example, the Solana plant in Arizona, which is a 280 megawatt plant, is using wet cooling. It's taking agricultural land and reducing the amount of water that was being used for that by a factor of 9. Now, there's another issue. Do you want to take agricultural land out of production? But that's a different story, so I won't go there. Let's talk just a little bit about the 3 fundamental architectures. The 3 fundamental architectures are line-focused systems, where you're focusing the energy along a line. That's the parabolic trough, and then there's a derivative of it called the continuous linear Fresnel that I have a picture of a little later that I'll show. Central or power tower systems. Central systems, you are focusing all the energy to one location from the collectors over the course of a day. And dish systems, which track in 2 axes. These both track in 2 axes, both in azimuth and in elevation, whereas the trough typically is oriented north-south. I have no idea which direction's north, so I won't even pretend. But it's oriented north-south and tracks from east to west over the course of the day. Some people would say, well, why wouldn't you orient a trough east-west and track it north-south? Well, you could, but because the sun is off-axis a lot more in that configuration, you get a lot more losses from the ends of the trough. So it's an optical issue. And you see some of the characteristics of them. I won't go through all the details here. This is a 2D shape. It's a parabola in 2D. These heliostats typically do have a curvature to them. It may be very small, but for a very large plant, that's needed. And the dishes, of course, are 2-dimensional paraboloids of revolution. Concentration ratios pretty much increase going from left to right. Typically, the temperature, the operating temperatures also increase. The two don't necessarily go hand in hand, but it happens to be the case here. By the way, if there's any questions while I'm going, it's fine to ask. I hate for somebody to miss something that they don't understand during the presentation. And we won't get involved in a long dialogue right now, but I'd be happy to. Oops, I guess you're going to know which button's which. Okay, so what I'm going to do now is take you through a little bit of a walk rather quickly through the development of CSP plants. These are the CEGS plants. Whoops, again, I got the wrong button. CEGS plants that were built in California between 1985 and 1991 by the Luz Company. And they were enabled by an incentive program that occurred under PURPA, the Public Utility Regulatory Policy Act, that encouraged renewable energy. Unfortunately, the only place this took hold was in California, and California picked up the ball and ran with it pretty well. They built 354 megawatts of plants. They were limited in size to 30 megawatts apiece by legislation. So they couldn't build big, cost-effective plants. They had to build, each one had to be self-contained, have its own power block. And that really doesn't make a lot of sense when you're trying to get the lowest cost production. They were also allowed to use 25% natural gas. So they're not full-size plants. They were able to cut back on the size of the collector fields because of that 25%. Now, under these contracts, they were rewarded for producing power during the peak times of the year when power is needed, the July, August, September timeframe when the air conditioning loads are highest in California and elsewhere in the Southwest. So they use that 25% to help them make it more possible to generate electricity during that period of time. Their efficiencies were a little low even for a trough at around 12%, solar to electric conversion. The next step in the U.S. that happened was Nevada Solar One in about 2007. What enabled this? Well, renewable portfolio standards in the West, a lot of incentives being provided by the states, a lot of pressure from state legislatures. Have you talked about renewable portfolio standards? They're a policy tool for trying to encourage the utilities, beat them over the head is more like it, to go to renewables because that's the direction that politically we think we should be going. It's a way of requiring the utilities to move forward. Actually, at the beginning, it was very much a contentious relationship about this. The utilities would put out requests for proposals. They'd come back and say, all these things are too expensive, we can't do that to our ratepayers. And then the respective regulatory commissions would review that and say, you know, you're wrong, you got to move forward with this, we're going to hold you to it, you're going to have to do it. So, and eventually they got on board and they started doing things. And it's a much more workable relationship today. This plant was the first one built in the U.S. since the CEGS plants had been built. It was enabled because in the intermediate time, during the early 2000s, Spain made a great decision for Spain. They looked around at all their resources, and all they have is, I think, one nuclear power plant, maybe two, and a couple of coal plants. And they import all the rest of their energy needs. And they decided that they didn't want to do that any longer. So they started with a feed-in tariff for wind. And a feed-in tariff is an agreed-to situation where the government says you will buy every kilowatt hour of electricity generated by this technology for this much, for this period of time, and for this much deployment. So it limits by limiting the deployment, you limit the total amount that it's going to cost. But it also sets the market. The market is real. It's not negotiated. It's there. If someone comes in and gets permits to build a wind plant, or later CSP and PV and biofuels, and so they move forward. And by doing now, the CSP number they set is very high. They set a number of equivalent 46 cents per kilowatt hour U.S. And that's about 3 times what we could even consider paying in the U.S. for CSP power. And that's what they did. And you'll see later, as I get into a discussion of what's been deployed and where, you'll see how much they've deployed. They surpassed us this last year in total deployment at a little over 500 megawatts of CSP deployment. And they're still building. Well, we're building too now. We've got 4 plants under construction. I'm getting a little bit ahead of myself. So, now the way these plants work, a trough plant works, is it uses a synthetic oil as the working fluid in the field, and you pump that fluid through the receiver tubes, which are dark tubes insulated with a glass cover, and the tubes have highly selective absorber surfaces. They absorb the solar energy spectrum and have a low emissivity for the infrared. And so they heat up the oil, and then from there on, it's a conventional power block. You simply pass that oil through a steam generator, it generates steam and drives a conventional power block, Rankine cycle power block. Conventional. The only thing that's different here is the steam generator and the oil loop in this plant. The Andasol plants in Spain, I mentioned Spain a minute ago. They're driven by the feed-in tariff. This plant was, whoops, too many buttons, Jaya. This is way beyond my ability to handle. They were limited to 50 megawatt size, capital investment of about 300 million euros. They have thermal energy storage in the form of 2-tank molten salt system that uses a sodium potassium nitrate salt. And they have about 28,500 tons of molten salt in this plant to get 7 full load hours of storage. They went to this because they could and because it increases the revenues from the plant more than it costs them to put it in. This particular storage approach is similar to one that was used and proofed by the DOE program at Solar 2 near Barstow back in the 90s, where we had built a molten salt power tower. And we had a hot salt tank and a cold salt tank. And I'll show you how that works when I get to power towers. But they're using a similar setup here where they can either heat the salt in the cold tank with the fluid, go straight to the power block, or even split off some and put some energy into storage while at the same time driving the power block. Now, molten salt has an advantage in that it addresses some of the issues related with renewable energy. Now, when you think of these thermal plants, one of the inherent issues that's very good about them is they're big. They have a lot of fluid in them. The fluid tends to have thermal inertia, so the sun can go away and you can still generate power for a while. Nevada Solar 1 can generate full load power for about a half an hour after it loses sun. So that's one of the advantages to thermal storage. The other advantage is probably more important. It totally decouples the collection of the energy from the production of power. So you can dispatch power when you need it. And that's where it has higher value. It's potentially lower cost because incremental turbine value costs decrease as you increase the size of the project, while the storage costs increase slower. The 2-tank is sort of the approach right now, although there are some options there. I'll describe the power tower later. Okay, to kind of clean up on the linear focus approaches, this is a continuous linear Fresnel approach. It uses a lot of small linear mirrors. Some are focused slightly, some are not, depending on the provider. I think these are focused a little bit, these are not. They're two different systems. And they focus the energy up onto the receiver that's fixed. The thing that tracks are the mirrors at the bottom. The thing doesn't rotate. The mirrors at the bottom simply track the sun and reflect it to the receiver. There have been two small what we refer to as integrated solar combined cycle type plants done with this one small one in Australia. And there's another one called Novatec where they're in Spain where they're doing some work. Now, the advantage to this, it approximates a parabolic trough. It's not truly optically a parabolic trough. There are some losses associated with this approach relative to a parabolic trough approach. But the potential advantages are that it gets all of the mirrors down out of the high winds when the wind blows, and anybody who has done any solar concentrator design knows that your big design is, number one, it's got to focus. Number two, it's got to focus when the wind blows and you can't get blown down. So the wind loads turn out to be one of the main drivers in the design of troughs, towers, and troughs, heliostats, and dishes. Okay, so Solar 2 was the first molten salt power tower. It was really just an experiment. It wasn't a commercial system. It operated for about 3 years. It demonstrated the efficiency of this two-tank thermal storage approach using a mixture of sodium and potassium nitrate salts, which is fertilizer. And it also demonstrated an external efficiency of 88%. Now, the way it operated is that you had a cold tank of salt. Now, this salt is always in the liquid phase. So what happens is you heat it up initially and melt it. It melts at about 220 C. And so you heat it up, and maybe you heat it up to 250 C, and you put it in the cold tank. Now, what happens then is when you want to collect solar energy, you pump it through the receiver, and you heat it up to 565 C and put it in the hot tank. All right? So it might be that one way you would operate the system is that you need the energy at from 5 to 9 o'clock at night because you're in Las Vegas like Solar 1 is, and that's when their cooling loads are highest. So what you do is all day long you heat up that salt, store it in the hot tank. Then at 5 o'clock at night, you may still be collecting some when you go ahead and continue to do that, but then you start to pump through the steam generator and you crank up the power block and you start putting power on the grid. Okay, so that's the advantage to dispatchability. One of the things I didn't point out on the troughs is that they operate at a different temperature regime. The oil starts to degrade at temperatures of about 400 C, so you don't want to push it over that. So when you do a two-tank molten salt for oil, you may have noticed on the Andesol, its high temperature was 380 and its low temperature was about 250. Okay, so this is always a liquid. It's sensible heat storage, so the delta T is directly proportional to the amount of mass you have to have. So you have to have a lot less thermal mass here to collect the same amount of energy that you would have to have for a trough system by a factor of 2.5 to 3. There are 2 commercial power plants operating in Spain today, the PS10, and I don't know which is which here. One is twice as big as the other, and I'll be darned if I can tell which is which. I think this is PS10, and I think this is PS20 because that's got the taller tower. They're once-through-water steam systems. They're relatively low temperature and relatively low efficiency. They were built by Abengoa with some support from the Spanish government. You can see some of the details. It's a once-through steam boiler, and I'll show you a schematic in just a minute. So the way they operate is that they pump water through the receiver and generate steam and then use that steam to drive the turbine. They also store a little bit of it to get a little bit of steam, and steam storage is very expensive to do, but they're doing it because they want to mitigate some of the intermittencies they have. The solar regime in Spain in general is lower than we have available in the southwest U.S. They're about equivalent to West Texas, actually, when you get down to it. I always found that interesting. But the way they operate this system is they pump water through the receiver, generate the steam, and then either put some of it to storage or send it directly to the power block. So it's, again, as I said, this is rather expensive storage because it's hard to store high-pressure steam for any length of time, and the cost of the tanks is relatively high. This shows the tanks and gives a little bit. The system operates at about 40 bar 250 C. That's generally the operational point of the system, so the Rankine cycle isn't even very efficient. They're looking to go to higher higher temperatures and pressures in the future. I put this one on here. It hasn't been built yet, but it is under construction now, and this is the BrightSource plan for their plants at Ivanpah, down about 40 miles from Las Vegas. They too are water steam systems, but they operate at a much higher temperature. That's not a minus 550, by the way, that's just a dash. They actually do superheat the steam in their receiver. And they actually have a very sophisticated heliostat tracking approach to create parts of the receiver that are superheaters, parts that are evaporators and preheaters and so forth. So we spent a day with them in February where they described the details of a lot of the things they were doing, and it's impressive the amount of engineering that they've done. Their first plant will be a 130 megawatt plant. I believe they've got some of the financing closed. I don't believe they've completely closed on their loan guarantee. Their plan is to have it operation, the first one by late 2012, early 2013. eSolar has built this modular power tower a little bit different than the classical power tower approach. A lot of very small heliostats, 1 meter square. They're modular in that they use these two fields then to heat this receiver, and they would assemble them in modules of this size. They too are operating at a higher temperature, but I guess I didn't put it up here, but they're not quite up to the temperature of BrightSource. They're more in the 750 C range. The change in approach is very interesting, and I guess, did somebody tell me they'd seen Bill Gross recently? Or, yeah, Bill Gross has been through it. Of course, this is one of his companies.
What was the temperature, did you say?
I think it's about 750 C. You know, you can't hold me to that, but I'm pretty sure I'm close. Because they're not operating quite as high as I'm sorry, did I say C? 750F. There, thank you. Thank you. Yeah, I was going to say they're not operating quite as high as BrightSource, which is 550C. Yeah, it's more like 750F rather than 1000F, and that leads to some. They also have to ship their steam to a centrally located turbine. It makes it hard for them to use a reheat cycle. Reheat cycles are real important in these low temperature turbines, and in fact, in any turbine, they buy you quite a bit of efficiency. So that's one of the disadvantages here. But they have some interesting approaches, and they can get to mass production very quickly with these small heliostats. Got some very clever things they're doing relative to tracking, and their business model is a bit of an enigma to me. I don't quite understand it because they're not a developer. They're selling technology, but they're not even a provider. They're kind of a consultant in the process, and will help the EPC put the plant together and so forth. And they're working with NRG, and I don't know where they are. They have one. I think they have one project pending in Antelope Valley right now. They've assembled at least a module, maybe two, in India. And apparently that was quite a learning experience for them. This is the first molten salt power tower that will be built. It's in Spain. It is built at this point and it's going through checkout. I received an invitation to the dedication with a question mark on when the date would be, but I'm supposed to save the date. This is it's being done by Senair and partners. It's called Hema Solar. It looks just in concept just like the Solar 2 schematic I showed you. It's 2-tank storage, large heliostat area, tower height 150 meters. Oh, this is one of the issues that comes up as you start to build these bigger plants. The tower height on a power tower goes up, and it starts to become an issue for where you locate relative to airports, and whether, if you're putting one up in Nevada, whether the Nevada test site pilots like the idea of a big tower out there. And so there are a lot of issues that come up. There are also issues like that you wouldn't think of, or maybe you would think of, glint and glare that might come off of glass or off of a receiver even. And we've done quite a bit of work quantifying that. It becomes qualitative at a point, but you can quantify the potential to do damage to the eye, and we've done some work with that. We're now doing quite a bit of consulting to the FAA and the Air Force over on how to evaluate some of these projects. Yes?
Storage capacity 15 hours, is that at rated capacity?
I believe so. I believe that's correct. You might be able to find out more about that by going. This is available on the web, by the way. It's called GEMASOLAR, GEMASOLAR. And you can see here it's operating between 290 and 565, so they take advantage of that. The third architecture is the point-focused distributed, where the dish tracks in 2 axes and typically has a receiver generator, engine generator located at the focal point. This is the SES dish. There's a 1.5 megawatt system in Phoenix, 60 dishes, been operating for a little over a year. They produce about 25 kilowatts. Peak system efficiency has been measured a little over 31%. Average efficiency over the course of a year is on the order of 24-25%, solar to electric conversion. These guys have gone through a downsizing recently. The financial crisis hit them a little hard. They're trying to figure out what they're going to do. I'm not quite sure where this fits in the scheme of things. I really think, it looks a lot like some sort of tracking PV system, doesn't it? And when you start thinking about an engine and a generator and mechanical parts versus a passive PV system, then there are trade-offs that you have to evaluate. They actually have excellent reliability on these things, but whether you can sell people on that or not, I don't know. Yes?
What is the temperature at the focal point of that?
The temperature at the receiver here, it's all a function of how much heat you're removing. You understand, if you don't remove any, it gets really hot and melts everything. The temperature is it's between 750 and 800 C. Okay? The actual hydrogen working fluid's about 750 C. So the receiver's a little higher temperature. These are smaller. These are the 3 kilowatt Infinia dishes. Again, 3 kilowatts, 25 kilowatts, takes a lot of them to make 100 megawatts. And what do you don't have any storage capability with them. They do respond relatively quickly, not as bad as photovoltaics in terms of dropping off when the sun goes away. They will coast for a while, maybe 30 seconds to a minute. But how do you handle that? We're currently working with these guys to look at some thermal storage approaches that might give them short-term thermal storage. That may be enough to make them extremely viable. Okay, so summarizing, I kind of summarized what my points are on each of these technologies. The trough systems, the steam power towers, which to date, we don't have one operating at very high efficiency because this temperature is so low. The dish Stirling systems and the molten salt power tower. Let me summarize my status. Trough systems are the most commercially mature. There's no question about that. They were enabled by the LUZ projects at CEGS back in 85 to 91. The experience in Spain allowed us eventually the first plant since the last LUZ plant to be built in the United States. If Spain hadn't happened, we wouldn't have Nevada Solar One. The company that built Nevada Solar One has about 5 plants in Spain right now. It's Acciona, it's called. It's a Spanish company. As you might expect, most of the big players in this technology are Spanish. So you ought to learn Spanish if you don't know it. Okay, but there's Acciona, Abengoa, Sener, ACS Cobra. They're all Spanish-based companies. But of course, most of these companies are pretty big companies too. And that means they're global in reach. And so they have, many of them have operational units here in the U.S. Dish Stirling systems are capable of the highest solar to electric conversion efficiency. That's a given, and my guys want to keep going on this and keep setting a new record every day, that kind of thing. Molten salt power towers really most effectively integrate thermal storage into the operation of the plant. It's the working fluid that goes through the receiver. It's in the storage system. It There's no heat exchanger required between those two processes like there is in a trough plant. The temperature of operation is high, so you get a high power block efficiency. It just all seems to come together in a molten salt power tower. And I'll admit I'm biased.
How high could you push that before the salts decompose?
That's a really good question, and it's one of the things we're going to be looking at over the course of the next few years. The guys tell me that we can probably go to 650 C with an oxygen blanket. And that buys you quite a bit. There's some talk of maybe going as high as 700, but I'm not sure that's true. But I'm going to talk a little bit more about that. Yes?
Do you know of anyone using intermediate pressure and temperature storage halfway down the temperature scale?
I do not. I'm not sure why that would be an advantage. Perhaps we could talk about that later. There's no simple way right now to integrate thermal storage into a dish system. We're looking at that a little bit now. Trough systems currently are using the two-tank molten salt storage in Spain, and the Abengoa plant being built in Arizona, Solana, will have molten salt storage. The power blocks in trough and power tower systems currently utilize wet cooling. Some of them are moving to dry cooling. Dry cooling will work. I mean, it's available, it can do it. It does cost more. It does cost more, so it increases the cost of the energy from the plants. Okay, so I'm going to shift gears a little bit from technology and talk a little bit about some other things like resource availability, cost, and so forth. Did anybody have a technology question they were dying to ask that they didn't get to ask? Oh gee, too many hands. Yes, go ahead.
Aren't there major advantages to using a natural gas host heater to get your operating temperature up?
Excellent question. And in fact, we have had a lot of discussions around that. We're thinking in terms of combined cycle and applications. That's really a very good possibility. Many of the solar people and many of the RPSs and many of the regulators have shied away from allowing us to use natural gas at all. Unlike the PURPA regulation, they want to, the utility says, no, I don't want anything with gas burning. If I want to burn gas, I'll do it in my gas plant. I don't want to do it in your plant. They don't consider the longer term implication of what this could do behind it.
When you quoted efficiencies, were they relative to land area or mirror area?
They were relative to solar in versus electric out versus solar in. Okay, purely.
But not the total acreage of the solar farm.
Well, how much solar, yeah, we can talk about that. Our friends, yes?
Do you know of anyone using multi-stage high-efficiency steam engines?
There have been people propose that. I'm not aware of any commercial applications, anything beyond experimental scale. Our friends at NREL do a lot of work on resource assessment. You've probably used some of the TMY data or something else if you've done any solar modeling. They do a really good job of that. This shows the DNI map of the southwest U.S. As I said, Spain looks a little bit like West Texas in terms of its resource availability. And you can see that California, this area right here, California, Nevada, has some of the better resources available. If you take that resource and you apply some filters to it, first of all, it's only direct normal. That's the first thing you got to remember. The second is we're only going to take the cream of the crops, something greater than 6.75. That is higher than Spain has. Spain only has about 6.1. If we exclude all sensitive areas, roads, lakes, places where you couldn't build anyway, and if we remove lands with slope greater than 1%, so you don't have to do much surface work and disturb the land, and you only consider contiguous areas of about 10 square kilometers, so you get a 100 megawatt plant. So we've eliminated a lot of space, guys. We end up with this map over here, which doesn't look all that encouraging, does it? Not compared to this one. Until we total up what a trough plant without storage could do on that land. If we look at it, let me bring you to the thought that the U.S. grid is a little bit over a terawatt right now in capacity, okay? And it generates about 4 million gigawatt hours annually. okay? If we look at all these states and total up what troughs located in those locations could do, the capacity would be approximately almost 7 terawatts. So almost 7 times the total U.S. capacity. Now, don't get me wrong here, we'd never do that. I mean, even if we could, we'd never do it, because how will we get the energy back east and whatever else? I mean, transmission enters into this in a big way. And if you look at the energy produced, it's about 4 times what what we use in the U.S. today. So in terms of resource availability and what we could do with it, you know, we may not be the only solution, but we ought to be part of the solution, don't you think? I mean, it looks to me like this is, you know, depending on cost, of course. Well, let's see, I mentioned transmission. And I'm not going to go into discussion, but there's a lot of things going on relative to transmission. Most of the projects that are being cited now are being cited at areas that have relatively good transmission location. But if you were to really make much of an impact, say we had a goal of doing 20% of the U.S. generation with these technologies, or with some form of CSP, then you'd have to have, or even with PV actually, because you're still going to need it. You're still going to need the transmission for PV. Then there's going to have to be a build out of transmission. And it takes a long time to build transmission. It's an incredibly arduous process. And there are people looking into it. Another thing that I didn't mention, but I'll mention in passing here, is that a lot of this land is BLM land in the West. It's owned by the feds. It's owned by us. Us, you and me, we own the land. Okay? And there are issues about siting projects on BLM land. We've spent a lot of time working with the BLM in these states, and they've actually set aside areas that they think are good areas where solar could be developed that wouldn't infringe on many of the other issues they think. Now, they put all kinds of conditions on it. For example, well, we still have to do our flora and fauna surveys and check on it, but we think this is a pretty good place to be. I mean, the conversation is going. The conversation is going. The first time I talked to BLM in Arizona, they said, we've got 32 solar projects proposed for land here in Arizona. We have no idea what we're dealing with. Could you come and tell us what these projects are about? I spent a day with them, and they said, oh, well, we've got all these projects. We know that this one's not going to go over here because there's a bighorn sheep migration that goes through there. There's no way those 3 projects could happen because they would interfere with that. And I said, well, did you tell that to the developers? No. Why not? They didn't ask. You know, the communication just isn't there. Okay, so what is incentivizing? The CSP is, let's see, my slides are out of order. I'm going to do this one first. Costs. There's currently an investment tax credit for large solar projects, 30% investment tax credit. That puts us in this rather broad, DOE likes broad regions, of where costs today with that 30% ITC are. That applies to CSP projects. In 2016, that 30% ITC goes back to a 10% investment tax credit and puts us on this curve. This is the curve without investment tax credit. You can see that we think we can get down below 10 cents a kilowatt hour. The yellow is the projected price of conventional energy resources from baseload coal and so forth. The pink here is California-centric. It's the market price reference, which is kind of the allowable cost that California defines. And it's actually a little different for each utility, so I'm not quite sure what they did in this case. But it's the allowable price where if you're below that with a renewable, they allow you to go ahead and use it. So let's see if I can go back. What are some of the incentives? I mentioned the 30% investment tax credit. That's a biggie. 4 projects got started last December because they're up through the first of this year. You get a direct Treasury payback of that 30%. Nobody has a 30% tax liability right now. There's very few of those guys available even when the money's available. There's a lot of investment money jammed up there somewhere. It's like a big water balloon that somebody needs to poke a pin in. And I'm not sure when that's going to happen. Another thing that's been very helpful is the DOE Loan Guarantee Program. Well, it's been helpful and it hasn't. The DOE Loan Guarantee Program says that you and I, again, we step up to the plate here. We're going to take large projects, and this is not just solar projects, this is wind projects, this is nuclear projects, nuclear power plants. We're going to, through the government, through the DOE, we'll provide an 80% loan guarantee on that project. So if it defaults, we pay for it. It's, and they're doing this with a pot of money that it's not stimulus money, it was actually authorized. Initially, the 1603 money was authorized under the Bush administration, and then the Obama administration had another authorization. But it takes forever to get through the process. It's worse than going to a bank. The people who do it talk about submitting stacks of paper like this and it taking 5 years for them to get partway through the process. It's just been terrible. They're starting to clear the way a little bit, and it's getting better, but it's still not good. There are state incentives. The renewable portfolio standards put the utilities at risk if they don't purchase renewable power. Many states have solar set-asides. A certain part of their renewable portfolio has to be solar. Some offer a production tax credit, property tax relief, and there are even local things. I've already talked about the feed-in tariffs, so I won't discuss that again. So the costs look like they can come down to be competitive. What'll get it to be competitive? Well, there's three pieces to that. One is R&D to improve performance a bit. This is incremental. The second one is convincing the investors that it's not as risky an investment as they think it is right now. And the way that happens is by deploying a lot of systems. And then by deploying a lot of systems, there's a heck of a learning curve. These guys really pick up and learn how to do it. They've shown us that in Spain. So those three things can bring us down to that area. This slide shows the amount of what's going on in Spain. And most of the sunlight's down here, but you can see there's projects all over. 582 megawatts operational now, 749 in construction, and about 5 gigawatts in provisional, and more elsewhere. If we look at what's going on operational worldwide, in the US we have 509 megawatts. You notice it was 582. They passed us last year, and at Solar Paces they made a big deal out of it. Made us feel bad. These are all the operating projects listed here. In the rest of the world, there's 609 megawatts. Most of that you can see is in Spain. 1068 are troughs, 36 are towers. So troughs, lowest risk, they can get the investment, they're going to do it. Troughs are going to be here for a while. And as they move down that cost curve, they're going to do well. Power towers, linear Fresnel, there's about 10 megawatts, and there's 1.5 megawatts of dishes. CSP project development, we have about 1,500 megawatts of CSP plants under construction right now today. That's 4 projects, the 4 I mentioned earlier, with another 6.5 gigawatts under development. With that, and you know, that may happen, may not happen. In the rest of the world, we only know that there are 842 megawatts under construction, most of it in Spain. We don't know how much is under development. Okay, so I'm going to shift gears and talk about where we might be headed, and why I feel this way. That the Secretary announced a while back the Sunshot Initiative, where he wants to accelerate and advance existing DOE research efforts by refocusing its solar energy programs. He wants to make large-scale solar energy systems cost competitive with subsidies by the end of the decade. He's targeting $1 a watt, or approximately 6 cents per kilowatt hour. And this is in the FY12 budget request. Well, we haven't even got the FY11 budget yet, so we don't have to worry about FY12 for a while yet. And what would CSP do in response to this? Well, we'd start to look at higher efficiency power cycles. Things like supercritical steam, supercritical CO2, higher temperature operation of existing cycles, the 650C somebody asked me about. We'd look at innovative ways of collecting that energy and get collector at more than half the current cost of concentrators. We develop, and we're, by the way, when I say we, I'm looking at a lot of we's in this room. We need a lot of help here. We need to identify other thermal storage materials that we can operate with at those higher temperatures. We need to identify materials that will contain and sustain that. We need to develop collection technologies that can be rapidly installed. The cost of installing and assembling a plant is significant.
Can I suggest fire brick?
Moving on, some of the R&D that we're doing right now is we're working on advanced helium. We've been doing this for a while. Advanced heliostat designs. We're now incorporating some other ideas. Again, I mentioned the high temperature cycles, heat transfer fluids, thermal energy storage. Looking at, you know, when you get to these higher temperatures, it's all materials issues. Can you still use carbon steel? Do you have to go to a high temperature alloy? If you go to a high temperature alloy, you might price yourself totally out of the picture. What are you going to do? How are we going to address it? These are real engineering problems. The economics are a big part of the issue here. Okay, I think that brings me to the end of my presentation, so I thank you for your attention. If there's any questions, I'll be happy to answer them. I'll stick around afterwards and jaw with you. Yes?
There's a couple of your comparisons that I had a question about. When you said the available resource is like 7 times the 1,000 terawatts of installed electric capacity, the installed electric capacity is electric. Your resource, did that include the solar to electric conversion?
Yes, it did. My estimate included a trough plant operating without storage, modeled on what that resource available was and the electricity we would get out of it.
So what conversion factor or what efficiency did you assume?
Oh, didn't assume when we ran a model. It was probably on the order of 14% solar to electric conversion.
The other question I had, when you showed the cost curve with and without government support, the conventional cost curves, generating cost only without transmission, centered around 5 cents per kilowatt hour, which is about 5. But now you have this constraint on location on the solar plants of any kind, so the transmission costs are likely to be higher. Did you make some allowance for that or not?
No, there was no allowance made for transmission issues, and you're absolutely right.
Okay, thank you.
Transmission issues are going to be issues for all of us in the future, for all kinds of technology. Yeah. Yes.
Is the thermal storage that you've talked about necessary to prevent plant damage to some of the high temperature?
Not necessary, not required. I mean, you could easily just run it, you mean like run a molten salt plant without those 2 tanks and just generate steam when you had enough heat? You could do that.
So do those generators ever have troubles because of high fluctuations in temperature?
Not so much because of that. We actually had one explode on us at Solar 2 because of poor design. But there are always those issues that you have to deal with in design. Because most of these molten salt systems are designed to drain back. In other words, you want to totally drain that heat exchanger, and you want to set it up to do that because you don't want that molten salt drying out and solidifying in there. Yes, yes.
Oh, yeah, I don't really understand why there's such a big divide between the CSP and photovoltaics. Like it seems to me like
There's no divide. There's plenty of room out there. It's very different technology. It's very different technology. The passive nature of the PV is very attractive. The distributed nature of the PV for individual homes and so forth is very well accepted. I don't think there's a divide. I think what there is they're really looking at very different markets, although PV is now looking at utility scale markets as well. and thinking that that's a really good approach for them, and it may be. So I'm not quite sure what you mean by divide.
You know, a project is either a PV project or a CSP project, but couldn't you take a site and combine both technologies and kind of make the most of the resource?
I'm not quite sure what you mean. I'm not sure how you do that. If you put fixed panels of PV up in the middle of a trough field, for example, you'd be shadowing the troughs. So, you know, I mean, there are, Abengoa, for example, has a lot of PV at their site in Spain. They do PV also. But it's, you know, often it's in its own field. It's not mixed in among. It's hard to do that because you're trying to get the packing density up so you don't want any shadowing.
Right.
Okay. Yes.
I think this gentleman in front of me, Mike Voss of General Electric, their turbine design states that large turbines have an operational life of 1,000 starts.
That's true for conventional turbines. Well, and for conventional, they're actually working on designs that will have more starts and smaller and quicker starts as well. There are some things you can do, and actually GE is working with us right now. Did I have a hand over here somewhere on this? Yes.
Yeah, I was going to ask more questions about contrasting PV and concentrating, in particular whether you had a feel of fixed panel, one axis, two axis, and as you get into these utility scale projects, how the arithmetic might pencil out, and where you think concentrating sort of does it have a sustainable long-term price advantage, or?
I'm inclined to think so, but I've never really done that comparison. I do believe that single-axis tracking PV is probably going to give you about as much power as, you know, if there's anybody that does CPV, don't kill me. But I did some work recently working with a CPV company, and it looks to me like single-axis tracking PV, because it can make use of the diffuse component as well, the concentrators cannot, that the cost of electricity from it is probably likely to be lower than from a CPV project, just based on the balance of plant costs. And that's really the only comparison I've done. The issue around not having storage in a PV system and the intermittency. Now, I will tell you this, and I don't know if you're aware of it or not, but if you have a really large field of photovoltaic concentrators, then the intermittency becomes less of an issue, because typically only part of the field will be shadowed at any time if it's large enough, unless, of course, the whole sky is dark. So there are some advantages to large fields on the intermittency issue, and I think that's pretty well been documented. Yes.
So California's about to pass a 33% renewable portfolio standard by 2020.
Yeah.
Do you have any concerns from a reliability standpoint that the grid will be as robust once we get there as it is today?
I think people will tell you today the grid's not as robust as it was yesterday. We've been extending the life of our coal fleet forever. We're making the solution, if you look at it, the only kinds of plants that are being built are natural gas plants, and we're burning expensive natural gas. It's an incredible feedstock for a lot of other applications that we need in our chemical industry. We're using it to burn as fuel. No, I can't speak to that. But I think we're headed to a lot less reliable future no matter what path we take, and taking no path isn't going to help us.
Okay, well, I think we're out of time, but thank you so much.
Thank you.
And, we have the Energy Social
For more, please visit us at stanford.edu.